Hello, everyone, and welcome back to your channel of Math Made Easy. We started probability last session, and we talked about some, like vocab words and, some operators like and, or, and not. Today, we are going to take a step further and discuss conditional probability. So, what is conditional probability? It means you have more than one event. One of them, you already know it happened. Okay, either you've seen it or somebody told you or whatever. And now, does that knowledge affect the probability of other events? Okay, if it doesn't make sense, that's fine. But sometimes they have nothing to do with each other. Okay, and if that's the case, we say they are statistically independent. Independent meaning they have nothing to do with each other. For example, I'm going to give you an example. Suppose I'm going to ask you, what is the likelihood, what is the probability that you get, say, a jack if you take a card from a deck of cards? I say, oh, don't tell me. What if I tell you that the card I selected was of the heart suit? So it's heart. You say, what are you talking about? It's the same thing. You didn't help me. Okay. Because originally there were four jacks in 52 cards. Now there is one jack in 13 cards because now we are talking only about one suit that has 13 cards. And 4 over 52 is 1 over 13. So I really didn't. I said, oh, so that knowledge, these two events were independent. I don't care. I'll give you one that sometimes I use with my students to make them laugh. And I say, okay, I'm going to roll a die. What is the likelihood that I get a four? Don't answer. Don't answer. I know you know it, but there is an extra piece of information that may help you. You said, I don't need help. I already know the answer. No, but listen, bear with me for a second. I forgot to tell you that before rolling the die, I tossed a coin and I get a head. Now, what is the likelihood that I will get a four when I roll a die? And they look at me like I'm coming from another planet. I don't know anything. And they say, this guy must be dumb. What does that have to do with it? I say, okay, now you put your hand on what we call independent events. They have nothing to do with each other. Now, let's go now and check a very simple case. I'm going to give you, well, two cases. In the first case, let me draw it on the left. I have my sample space, and my sample space contains only two events, and they are mutually exclusive. They have nothing, they don't overlap. Okay. And let's say this is event A, and it has a probability of 0.2. And here is event B, and it has a probability of 0.3. Be careful here. Originally, I say the probability of A equals 0.2, right? Listen, when we use conditional, we use a pipe. So we say, what is the probability of A given that you already know B occurred? And what is the probability of A given that you know B didn't occur? Think, take your time, pause the video, think about it, and tell me how these are related. Are they related? Are two of them equal? Are they all different? How did you figure out? Okay, I hope you paused, thought about it, and now you have an answer. The answer for this guy, if B occurred, then you know the probability of A given B would be zero, right? If B occurred, so how come A occurs? They don't overlap anyway. And what if I say what is the probability of A if you know that B didn't occur? And many students, unfortunately, they say it stays zero point 0.2. But is it? Well, if you know that B didn't occur, your sample space is no longer S that has a probability of 1. Do you see that? Point 0.3, it's like you cut point 0.3 from here and the remaining is only point 0.7. So the probability of A in this case would be zero point 0.2 out of zero point 0.7 or 2/7. So roughly it's almost 30%. So while your prior knowledge about A was 20%, if somebody told you, oh, I got B, and you know that A and B are mutually exclusive, then A now becomes zero. It drops to zero. Okay? And if you know that B didn't occur, now the probability jumps from 20 to roughly 30%. Okay. And then you say, it seems complicated. You say, no, let's take another case. Let's take another case that may uh, is slightly different. I'm going to take the same two events. Maybe I change the numbers. It's boring, you know, zero point 0.2, 0.3, whatever. But it doesn't matter. We can pick. Well, let's see. So here is event A, and here is event B, and now they are overlapping. And let's say A was, let's say the A was 40% and B was 30%. Or we already, it doesn't matter, 30%. And the overlapping is 0.1, meaning this is 0.3 and that's 0.1. This is 0.2 and that's 0.1. Okay? Now, listen carefully. Still, here, probability of A was originally 40%. We call that the prior probability, but it doesn't matter. We'll talk about these in more detail later. Now, stop the video again. Think about what is the probability of A given B and the probability of A given not B. Okay. Alrighty. What is the probability of A given B? So if you know your B is here and B occurred, what is the probability that A also occurred? If you say 1/3, you would be right, because now your sample space is no longer the whole thing. It doesn't have a probability of 1, but your sample space is 0.3. And that usually gets in the denominator. And then you say, oh, but if B occurred, there is a probability that A also occurred, but this probability is only 10% of the whole thing. So zero point 0.1 over 0.3 is 1/3. What if you know that B did not occur? So if B did not occur, this whole area is cut, and because we picked the same number, so the denominator would also be 0.7 like before. But now, what is the likelihood that A occurred? If you know that B did not occur, so this part of A definitely didn't occur, right? So the remaining probability of A is only 0.3 out of zero point 0.7, so it becomes 3/7. So it increased from 40% slightly to roughly 42.9 or something. But if you know that B occurred, it drops from zero point 0.4 to 0.333. And you say, okay, but Is there a way to describe it easily instead of drawing the Venn diagram, looking at that? Before I answer this question, and that would be a good question, my always I tell my students there is no such thing as a non-conditional probability. All the probabilities in the world are conditional. And what is the condition? Let me rewrite it. Let me rewrite PA. I'm going to say the probability of A, but instead of saying given B, given whatever, no, given S. So it's like I'm telling you, what is the probability of A if I tell you beforehand that we got something inside of the sample space? And you say, that's so dumb, right? Because the sample space will always occur. So why are you telling me that? I tell you, but wait, bear with me for a second. I can redescribe that as the probability of the intersection of A and the sample space divided by the probability of the sample space. See if that makes sense. So if I have any sample space, be it the whole thing or part of it, what I need to do is to say the probability of A and the corresponding sample space divided by the condition, which is the sample space. Now, the condition is 1, right? What is the probability that you get something inside the sample space? It's 100%. Likelihood is 100%, meaning the probability is 1. But now, what is the intersection of A and S? What do they have in common? They have in common A, right? So you get A over 1, which is A, which is, I'm sorry, the probability of A, the probability of A. And that's why we don't write it this way, because it's trivial. What is the intersection of any event and the total sample space is the event. And what's the probability of the sample space? It's 1. And that's why we don't write it as a condition, but it is conditional. But it's a trivial condition, right? What is the probability that something inside the sample space occurs? That's the definition of a sample space. Nothing can happen outside of it. But if you think about it this way, I can rewrite the probability of A given B as the probability of A and B divided by the probability of the condition, which is B. What is the probability of A and B? A and B is 0.1. And what's the probability of B? The probability of B is 0.3. So you get the same answer. So you don't need to draw the free body diagram. If you know these probabilities, you don't need to draw the Venn diagram and no, just use that. What is the probability of A given not B? Well, if B is 30%, then not B is 1 minus that. Because in probability, the probability of an event plus its complement, the probability of its complement is always 1 because you are either in A or not in A. Notice that this is not like when we do, for example, um, um, when, okay, I don't want to go into that. I don't know if you would even have heard of it or not, but um, if we use fuzzy logic, if you heard the term before, there is something that we can say it occurs and it didn't occur. It's like, for example, let me give you my wife and I, okay? She loves hot weather. I like cold weather. So we set, say, the thermostat of the air conditioning to, let's say, 74. She's comfortable, and we ask her, is it, hot or cold? She said it's okay. For me, it may be a little hot. So you see, there is a, well, again, if you already learn anything about fuzzy logic, you would understand what I'm saying, but forget it. In probability, it's either in or not in. There is no such thing as an overlap between these two. So if the probability of B is 0.3, then the probability of not B is 0.7. And what is the probability of A and not B? If this is A, And everything outside this is not B. The intersection between them is that part, which is zero point 0.4 minus zero point 0.1 or zero point 0.3, and you get 3/7. So now, if we rewrite it, and the probability of B given A would be the exact opposite. You would divide by the probability of A instead of the probability of B. But let's write this again. I'm going to give you new vocab words now to use that we may use later. Next to that, I'm going to write the probability of B given A. It's the probability of B and A, but there's no difference. Let me write it the same way as that. But now I divide by the probability of what's after the line or the pipe, you place it in the denominator. You would say, wait, I can represent the probability of A and B in two different ways? Yeah. Which means if I cross multiply, I can get the probability of A times the probability of B given A is the same as the probability of B times the probability of A given B. Both of them would be the probability of A and B. And you say, does that help? Yeah, I will give you some examples to see. But before I do that, I'm going to refer, we already know that this is the conditional probability. This is called the joint probability because it's a joint, two events are joint and occurring at the same time. So we call it joint probability. And the denominator, you will learn it later, that we call that the marginal probability. I shouldn't have written probability here only, but that's the scenario. Now let's take this and have, coming back to this page, so I'm going to leave it here and then take an example and see what is going on. Why sometimes I write it like this and sometimes like that. We'll see. We'll see that in a second. So in this example, let's draw again a Venn diagram. For example, well, let's extend it a little bit. Doesn't matter. Didn't have to, but okay. Let me divide that into 1, 2, and 3, not necessarily equal areas. In our plant, we are producing some widgets to sell to gullible people, you know. And we only have 3 machines in our shop. This is machine 1, that we are going to call it machine A, that produces, it seems like it's almost 50, let's say 40% of our production. Machine B, or machine 2, produces, let's say, 25% of the production, which leaves C, which is machine 3, producing 65, so 35% of the production. Okay? Now we tell you that, so this is the machine 1, or ABC, let's say ABC. And defect, or the defective percentage, okay? So each one has different defective percentage. Let's give some numbers. So let's say this is 4%, this is 2%, and that's 3%, whatever. And I'm asking you, okay, can you find the defective percentage for the whole production? Think about it and see if you can come up with something that makes sense to you. Okay, whether you pause the video or not, what I'm going to do is to draw something, another event that cut across all three machines. And maybe I should have used a different color, but it doesn't really matter. I'm going to say this is the defect. So I'm going to use the letter D for, so we have ABC, so A, B, C, D. D here is the defect. I know these three. I don't know what I call them. If I call this machine A, so for example, if I say the probability of A is 40.4, probability of B is 0.25, probability of C is 0.35. Notice that when we add them, you get the 100% because your production comes definitely from one of these three machines. By the way, we call A, B, and C. Remember, we used a term before in the first session. We call them mutually exclusive because they don't have anything overlapping. So mutually exclusive. But now we are going to add to it something else. So we learned three words here of in your vocab. Now we are going to learn one more. Mutually exclusive are like these two. But you see, there are stuff outside of these two. So they are only mutually exclusive. But here, you don't have anything outside ABC. So they are mutually exclusive and collectively exhaustive. Exhaustive meaning nothing outside. So that when I use one of these terms later, you don't ask me, oh, what do you mean? We already discussed that. Now, using what we discussed here, who can tell me, and this is probability of D, who can tell me how do I refer to these three percentages and how do I refer to these three areas using A, B, and C and D? Pause the video, think about it, and let's discuss why it makes sense. The answer would make sense. Okay, I hope you already have an answer. This is intersection, so you should get that easily. This is the probability of A and D. It's so small, so I couldn't write it properly. The probability of B and D. And this is the probability of C and D. Sorry, I should have drawn that in a larger way. But how do I describe those? If you got this one correct, you are on the right track and you would cruise through that example. This is the probability of anyone? D given A. It's the probability of D given A. Once you tell me given A, meaning if you tell me, oh, this item is coming from machine A, I say, oh, there is 2% chance it's defective and 98% chance it's not. It's good. Same thing, probability of D given B and the probability of D given C. Notice, in order to get the probability of D, the whole defective percentage coming out of this plant, of course, it has to be between 2% and 4%, right? And if you heard the term weighted average, you would understand it now, if it didn't make sense to you. Probability of D, it's basically from this figure, probability of D is the probability of A and D plus the probability of B and D plus the probability of C and D. right? A and D plus plus. Why do we say plus? Remember when we were talking about union and intersection? Here, it's a good way or good place to write it. When you have mutually exclusive events, events that don't overlap, if you have mutually exclusive events, if and only if you have, we write it IFF in math, meaning if and don't and only if, because mathematicians don't have time to waste writing, you know. Again, not like us mortal humans, we try to write everything in detail, but mathematicians would like, 3 points like that, or some symbols that they think nobody know about them except them. They tell you this and stuff like that. Okay. Maybe you will become a mathematician and make fun of us by trying to invent new symbols that nobody know about them except you. But for now, at least we figure out that IFF means if and only if. Okay. If and only if you have mutually exclusive event, then the or translates and is exactly equivalent to plus. Some people, when you tell them probability of A or B, they add them up. Remember, last session we realized that no, you add each one, but then you subtract the overlapping. But since mutually exclusive events don't have an overlap, then and only then, you are allowed to translate the or into plus. Later, we'll learn something else, maybe next session. Okay, now I go back here and I say, wait a second. The probability of B, I multiply A times the probability of B given A. So, can't I use the same logic and say the probability of D equals the probability of D given A times the probability of A? When I do that, what do I get? Remember, multiply conditional by marginal. You get the joint, A and D, which is this. Probability of conditional times marginal. Conditional times marginal. They give you the joint. So, plus the probability of D given B times the probability of B plus the probability of D given C times the probability of C. All three were in mutually exclusive, so the or, this, and this, or this, or this, these are the defect. It's either this or that. The or becomes plus, and then I use the conditional probability to solve, and now I can say probability. So it's 2% times 0.4 plus 3% times 0.25 plus 4% times 0.35 equals 0.008, right? Plus 0.0075 plus 0.014 equals, this would be 0.008. This is like 4 digits, so let's write the 5, and then 4 and 7, 11, 8, 19, carry over 1, and 1 is 2, and then zeros, 0.0295, almost 0.003. We know it has to be between these two numbers. If you get something below 0.02 or above 0.04, you did it wrong. So it's roughly 3% defective rate. Excellent. Now I'm going to give you, the $64,000 question. We were not paying attention. We were just collecting all the product and place it in a big, huge bin. And at the end of the day, We were collecting, just for quality control, we need to know is before sending stuff, we want to see if the parts we are sending are good or bad, defective or non-defective. So we pick one at random, and it turns out, let's say we'll do both sides. Suppose it turns out to be defective. And someone would say, what is the likelihood it came from John, the operator of machine one, machine A? Wait a second. What? What is the probability that it comes from machine A? Hmm. How do I know that? Meaning you already know it's defective. That's the given. That's the condition. So you want to find the probability of A given D. This is, by the way, is called the subjective probability or the Bayesian probability. In other words, you need to know Bayesian probability or subjective probability. I don't know A given D, but I know D given A. Guess what? Do you see that? If you know one, you can say, oh, if I want the probability of B given A, I would divide both sides by the probability of A, right? Same thing. So see how we are going to do it. Probability of A given D. Given that you know it's defective, what's the likelihood it's coming from A? You would say it's the probability of D given A times the probability of A divided by the probability of the defective. Now replace B by D. So if I want the probability of A given D, I would say it's the probability of A times the probability of D given A divided by the probability of D, which is that. So you invert those, multiply by the condition, which is PA, and then divide by that condition. Wait a second. I already know this guy. It's the first term. Coming from machine one, it's the first term. And I know this guy, it's the total. So it's 0.008 over 0.0295. And then I use my calculator and divide 8 by 29 and a half, or 0.008 over 0.00295. I get, oh, no, I must have done something wrong. Oh, I divide by an extra zero, right? 0.008 over 0.0295. And you get roughly 27%. Hmm. Originally, if I ask you what is if I pick one item at random and I ask you what is the likelihood it's coming from machine A, you would say, oh, 40%, right? But if I say, no, no, like I did with my students, I say, no, wait, don't answer. I picked an item and it turned out to be defective. Now, what's the likelihood it's coming from A? Now you change your mind because they are not independent, right? You calculate the weighted average, 40% of 0.02 divided by the weighted average of everything. And now another one that I want you to do on your own, think about it. I picked an item from that bin and it turns out to be perfect, non-defective. What is the likelihood it's coming from machine B? Let me see how you write it and then stop the video, pause it or pause it, solve it, and then come back. Take maybe 5 minutes or so. I want, again, I will repeat the question. We collected all the production into one big bin. I picked an item at random. Yes, it's non-defective. I'm going to send it to the customer. But the guy said, who did that? We want to commend the operator. And he said, I don't know. So we can ask, what is the likelihood it's coming from A or B or C? my question is, how do I find the likelihood that it came from machine B? Okay, take your time. We're back. Okay, I'm gonna write it as such, and somebody tells me if you already did it this way. I know that it's not defective. Not defective meaning D prime. And what is the likelihood it's coming from machine B should be the probability of B given D prime. So I'm going to say it's the probability of D prime given B times the probability of B. And then I divide by the probability of D prime given A times the probability of A plus the probability, three terms like that. But do I really need to do it? No, because if the probability of D, I want you to go back and redo these examples to understand that we really don't need to do any more work because we already know that the probability of defective is 0.0295 and the item can be either defective or non-defective. There is nothing else, right? Nothing else. So their probability should add up to 1. So this is 1 minus the probability of defect. Let's try to fill in the blanks. I know that the probability of defective given B is 3%. So not defective given B would be 97%, meaning the probability that it's coming from machine B. What is the probability that it's not defective? You'd say, oh, if it's 3% defective, that it's 97% non-defective, times the probability of B, it's coming from B, which is 0.25, divided by 1 minus 0.0295 equals. If you've done it this way, you commend yourself. You're on a like streak. Okay, 0.97 times 0.25 divided by 1 minus 0.0295 or 0.9705. Roughly 25 didn't matter. It almost came the same. It's just the numbers, but if you do it for A, so let's do all three quickly. So this is 0.2, let's say 0.25 to 2 decimal places. Let's do it for A. A would be 0.98 times 0.4 divided by, let's subtract, it's 0.9705. Instead of writing divide by 1 minus that, you get, oh my God, it's almost the same. I picked horrible numbers. And of course, for C would be 1 minus that. So it didn't change. Usually, if I pick, I know why most likely. You will get 34.5 instead of, or zero point 0.6 instead of 35%. It didn't matter. But if I were you, I will change these numbers. Okay, make that say 0.05, make that 0.01 and that 0.02 and repeat and see what you get. And maybe we can discuss that next time. I'm sorry I picked one that we ended up with the same. Usually, the original probabilities that we had, like the 40%, 25%, and 35%, are called the prior probability before you run your experiment and see if it's defective or non-defective. The probability of A given D or A given not D, depending on whether you are doing the defective or the non-defective for all three of them, is called the posterior probability. So there is a prior, but when you give a condition, that changes usually, not in this example. This was a horrible example. I should have picked numbers ahead of time instead of just making up numbers. Usually these probabilities will change and you will get what we call posterior. So prior and posterior probability. These are the vocab of the Bayesian probability. But we are not going to waste more time on that. Next time, we are going to talk about independence, statistically independent events. Don't go away, come back, and I hope you will like it. Thanks for your time and watching, and hope you all the best. Bye.